one thing that I would like to do better at in class is having useful visuals on the board for us. So I thought I'd start off with this one. Do you guys remember when we were talking about Unit 2 and the families? And I told you that hydrogen is kind of a stray, no family. I thought this was funny. I saved this on Instagram a long time ago. I've been waiting to share it. I should have shared it last week. But you'll see the alkali metals, and then Jerry trying to be one of them, right? And you could do the same thing, but do it with what other family? Not the noble gases, the halogens, group 7 or 7A or 17. Because hydrogen also likes to make one covalent bond. The alkali metals don't like to make one covalent bond. Hydrogen can take on a negative charge like the halogens, although it prefers more readily to take on a positive charge. So, thought that was cute. Wanted to share it with you guys as a reminder. I also, I saw this message on a student's post-test reflection. If you have not taken your post-test reflection, please do it. And I do want to point this out. Post-test reflection gets the same amount of bonus points as the pretest. So if you didn't take the pretest reflection, why would you not take this? It can't hurt you. It can only help. This student said, I thought having detailed notes would be enough, but I ended up spending too much time flipping through looking for things. Did any of you experience that on the unit test? That you were like, great, I get to have all of my notes for this, and then you actually killed your time because there was too much information maybe, or you weren't sure exactly where it was going to be. Having notes is one thing. Knowing how to use your notes is another. So if you have detailed notes, great. You may want to consider rewriting them or just copying them, because that process of reading, processing, and writing it out again helps ingrain it better for you. You might also want to consider just building a study guide, going through your detailed notes, analyzing them, picking out the most important things and putting it on a study guide. That way, it's a little bit easier to navigate. You can go through it a little bit more quickly. But if your notes did you well on that unit test, great job. All right, as we move into Unit 3, I wanted to share this video. There's no sound associated with this, but I don't know if I have control of the lights. Do you guys see what's going on? Gases inside of these glass tubes, and then there's electricity running into them from the bottom. And these gases are labeled by their substance. What do you notice about them? Different colors. So it doesn't matter the voltage, it's the same amount of electricity coming in. It doesn't matter the material surrounding them, they're all in the same type of glass. What changes the color produced? Sorry?
Was he touching it with his finger?
He was poking them.
Okay.
But poking them doesn't change the color, right?
Oh, sorry. I thought you meant the intensity.
You're right. The intensity was changing, probably based on contact. You could see that this is kind of loosely sitting in there. They dropped it at one point and it just bounced and bounced. The intensity changes, but what determines the color? What's in it? The substance, the chemical. So this is one of your main objectives in Unit 3. Understand the relationship between light and matter. This weekend I also worked on making this for you. I need to find it. I I may have lost it, actually. I'll come back to it at our break. I made a list of learning objectives with action verbs, similar to what you guys will see on Canvas when you go to one of the first pages on each unit. It'll have learning objectives, and one of the first pages on each section, learning objectives. But they're written in my words, based on my notes, so they kind of target what I expect you to get out of your notes. But moving into Unit 3, Module 5. Here we're looking at the electromagnetic energy, the electromagnetic radiation, electromagnetic spectrum. You guys remember our very first lecture, our first day of class? We spent some time talking about the 4 fundamental forces and electromagnetism being one of them. So we call light, colloquially, the thing that we can see. And sometimes even the things we can't see, like black light. Can't really see it, but you can see its effects. And so I want to be clear that in this class, we don't think of light as just something you can see. Light is electromagnetic radiation. And it's not just radiation, propagation of energy of one thing. It's the propagation of 2 things. We say that light is both a particle and a wave. And I don't want to be confusing. Those aren't the 2 things. The wave is what's propagating 2 things. This is a magnetic field and an electric field. We represent that with B arrow on top, E arrow on top. Magnetic field and electric field. What do we call the particle of light? Photon. It's okay if this is confusing to think of light as both a particle and a wave, but it turns out that things that are this small are very confusing. They don't obey our macro scale physics laws. So in this section, we will be talking about what laws they do obey. And we'll need to get comfortable with the things they don't obey that we can, and the things that they do obey that we don't have to. If we look at the wave aspect of the photon, there's a few points that we want to know. I'm going to draw this dotted line to try and go right through the middle of my wave as kind of a reference. From this center line to the peak or the trough is called the amplitude. Amplitude is the energy of the wave, but not necessarily the energy of the photon, because photons, being waves, can have constructive interference, where all of their waves sum together to give a much larger amplitude. So if I have one photon, and I'm looking at its wave, the amplitude is proportional to its energy. If I have 10 photons, and I'm looking at the wave that they all create constructively, then the amplitude is the energy of 10 photons. That's what amplitude is giving us. if I measure from peak to peak, we give this the Greek letter lambda, and of course this is called wavelength. At what point does the wave get back to that same height? True or false? You can only measure wavelength from peak to peak. Where else? Trough to trough. Anywhere else? Sure. Anywhere where the wave gets back to the exact same point. So if you want to say on the right-hand slope, then measure again to that same place on the right-hand slope. The wavelength is consistent all the time. And then there's one last component about the wavelength, and that is represented by this letter that looks like a V, but we call it nu, like new shoes, new year. Nu is what? Frequency. It's harder to represent frequency on here because frequency is measured in per seconds or hertz. So what I would need to do is actually put up some sort of moving graphic. But if I say that I have this wave and I start a timer here and I end a timer here, then I've moved 1, 2, 3 wavelengths, and that timer measured just 1 second. Then my frequency would be 3 hertz, 3 per seconds, 3 waves per second. That's the frequency of it. And then we have this relationship of the wavelength, the frequency, and the speed that the photon moves at, the speed that the wave propagates at. You all know C from Einstein's famous equation. E equals mc squared. The energy of something is equal to the mass of that something times the speed of light squared. That's the same C. And what value do we give C? 2.998. So I've seen different people round it differently. This is not a constant you'll have to memorize, actually. Let me show you where you'll find it. On your potentially useful equations, possibly useful equations for the midterm, you'll notice that C is up here. Oh, I stand corrected. You're not given C as a number, so make note of C then. 2.998 times 10 to the 8. Now, Ryan, that's where you left me off, but that's not quite the speed of light. It needs what? It needs units, actually. Good. How many significant figures in that speed of light? 4 sig figs. Good. And some people will approximate this to about 3 times 10 to the 8 meters per second, or 300 million meters per second. Does the speed of light change based on its wavelength? Does the speed of a photon change based on its frequency? Notice that was a weird thing to say because the photon is the particle, but frequency is a matter of being a wave. Does the speed of light change based on its frequency? The speed of light is constant. And actually, that speed is the speed of light in a vacuum. Light does travel slower in different media. It moves slower in water. It moves slower in glass than it moves through air. I think light moves slowest through diamond. It's one of the densest materials that light can move through. All right, so let's do some calculations. Let's practice applying these. If I have a wavelength, 242 nanometers, what is the frequency given that the speed of light is 2.998 times 10 to the 8th meters per second? Did any of you find out that you don't know your calculator as well as you thought you did on that unit test? Because calculations are not going away. So if you felt like you needed a leg up on your calculator exercises, find some time to practice that. You'll find it in this unit. What unit do I want to be left with at the end of my work here? Sorry? Hertz, which is per seconds. I haven't written it, but frequency has this unit per seconds, which is called hertz. Or if I want to, I could go to megahertz or microhertz or whatever I want to. To set it up, let's take the equation that we need. Notice that this equation is on your sheet, so you don't need to remember it. Sorry, you don't need to memorize it. You should remember it. But you don't need to waste space on your study guide either, or on your cheat sheet for the midterm with that equation. When you build your cheat sheet for the midterm, which I recommend starting after the Unit 1 test, because you want to write down what things from that test you want to put on the midterm cheat sheet, have this handy. Don't waste space on your cheat sheet with things that you're already going to be handed, unless it's examples of how to use them. So first, let's write out the equation. C equals lambda times nu. Second, do the algebra to solve for nu. Is the algebra here challenging?
No.
Why not? Divide what? Which term do I divide? Divide by lambda on both sides. And now I get C over lambda is equal to nu. Because lambda divided by lambda cancels out. Does it confuse you having the term you're solving for on the right? Then we can do algebra to flip it back. The algebra is as simple as taking exactly what is written on the left and writing it on the right, and exactly what is written on the right and writing it on the left. It's just its mirror image. This is the, I don't know, law of reciprocity or something. Being equal to each other means that you can write it on either side. So if this is the equation that you want to work with, great. But there is no difference between these two equations. Why did I do the algebra before I put in any numbers? Anybody? Makes it look cleaner? No, it wouldn't solve for a different variable. I know C and I know lambda, and I still have nu as a variable. But then I have to take C and lambda and do the algebra with them. And it's not rounding errors yet, actually, because I'm not doing any calculations. if I had 2.998 times 10 to the 8th meters per second equals 242 nanometers times nu, now I have to rewrite them every time. It really is just a matter of use the variables because they're more condensed, easier to read, easier to cross out. If you don't like that, step 3 can go after step 1. Plug in the numbers. Then do the algebra to solve for the variable you want. Doesn't matter. Plug in the values. We've got 2.998 times 10 to the 8 meters per second divided by 242 nanometers equals nu. Do you see a problem with this equation? And that is? Units. Units do not cancel. So I need to do one of two things. Convert meters into nanometers or convert nanometers into meters. Either one is totally acceptable. Which one do you want to do? Nanometers to meters? Anybody disagree? Now, I'm not reporting a number here, so I don't have to obey the rules of scientific notation if I don't want to. What order of magnitude difference is there between nanometers and meters? 10 to the 9. So, if I want to change 242 nanometers into meters, then I'm just going to do 242 times 10 to the, I'm going to a bigger unit or a smaller unit? Nanometers, tiny. Meters, relatively huge. I'm going to a bigger unit. My number should get bigger or smaller. Going to a bigger unit, smaller number. 10 to the negative 9 meters equals nu. Now, I want to show you what that looks like if you did it the other way. If you want to change meters into nanometers, then you have to do 2.998 times 10 to the, I'm going to nanometers, so I'm going to a smaller unit, bigger number. So I need to add 10 to the 9. 10 to the 9 times 10 to the 8, 9 plus 8. 17. Much bigger number, correct? Much smaller unit. Divided by 242 nanometers. Do you see how the units cancel? Meters over seconds divided by meters. Meters cancel. Nanometers over seconds divided by nanometers. Nanometers cancel. These both equal the same thing. They're just two different ways of writing it. So now we get down to our calculation. Plug these into your calculators. See what you get. If you feel comfortable with your exponents, then you can do that exponent math separate from the coefficient math. But if you don't feel comfortable with that, plug everything in. Did you check with Blake yet to see if he's got that too? Don't forget, if you've got that times 10 to the function, it can save you a little bit of time in getting things written out. All right, now, a lot of you should have gotten some answers already, but I want to check. Do you think this number is going to be very large per second or very small per second? And you can figure that out using the coefficients. Lizzie, you think very small per second? What is 10 to the 8 divided by 10 to the negative 9? With exponents, multiplication means you add the exponents. Division means you subtract. 8 minus negative 9, positive 17. What is 10 to the 17th divided by 10 to the 0? 10 to the 17th. This is going to be a very large number. If you get something that is very small, you've plugged in something wrong. That's a proof. Okay? What do you get? 1.24. Why did you stop there? And which one limits our sig figs? Good. Now I'm gonna show you what my calculator actually says. 1.2388, and it keeps going per seconds. And I'm gonna write that as just inverse seconds. But if you didn't want to, you could literally write it as per seconds. That is a correct unit. Nothing on top, per 1 second on the bottom. Oops, I forgot to put in my times 10 to the 15th inverse seconds. We were limited to 3 sig figs because of 244. Here is my third sig fig. What number is rounding my last significant figure? What number is rounding my uncertain digit? The 8 rounds it up. So my final answer here, 1.24 times 10 to the 15 hertz. And you can probably see why this is not the most useful value for us, right? Times 10 to the 15th. Maybe I can change the unit to get a smaller number. And that's where I want to show you this electromagnetic spectrum again that I have here. Not every electromagnetic spectrum, by the way, is oriented the same direction. You'll notice that this side of the electromagnetic spectrum is high energy, high frequency, and you'll notice that this side is low energy, low frequency. I'm used to seeing a lot that are actually flipped from that by having high energy here and low energy here. Just pay attention to the units. This electromagnetic spectrum compares the wavelength in meters to the frequency in per seconds, hertz. We started with something that was about times 10 to the negative 9th meters. That'd be somewhere around here. Then we moved to something that was times 10 to the 15th. That's about here. Either way, what do we know that we found? And I want to explain. It looks like we moved like this, 10 to the negative 9th, 10 to the 15th. But actually we were 242 times 10 to the negative 9th. So we were closer to times 10 to the negative 8th. We fell right about here. What range are we in? What kind of light are we looking at? Ultraviolet light. This is the kind that will damage your DNA and give you cancer. This is the kind that is mostly blocked by our upper atmosphere, absorbed by the ozone layer, transmitted into different forms of energy. Okay? Can somebody, actually before I put this away, can somebody point out another region of the electromagnetic spectrum you'd like to do a calculation on? Microwaves. Let's flip this in reverse. Let's take Let's take the frequency of a microwave. This is actually a cool experiment that you can do at home. If you take out that spinner in your microwave and you set a big chocolate bar on a plate in there, you will burn high intensity radiation into your chocolate bar, and you can measure that wavelength. That's where the nodes of the wave are actually hitting your chocolate bar. You can measure that wavelength like we just did and convert it to frequency, and then check the frequency of your microwave. Or check the frequency of your microwave, convert that to the wavelength of the light that it's emitting, and then put a chocolate bar in there and see if it actually is that wavelength. All right, let's see the frequency of most microwaves. 300 megahertz to 300 gigahertz. Let's go with this number, 242 gigahertz. Or was that 2 point? Thank you. 2.45 gigahertz is our frequency. We don't know our lambda, but we do know that the speed of light is 2.998 times 10 to the 8 meters per second. Can you follow these steps? Write it out, do the algebra, plug in the numbers, and solve for the wavelength. I want you to take about 45 seconds to do steps 1 and 2. Once you get to plugging in the numbers, I'm going to have you guys turn to each other and work together. All right, by now you should have gotten it written down, ready to plug in the numbers. Turn to the people around you and do this calculation together. See if you have the numbers set in right. Figure out how you're going to convert the units to match. And once you're done, tell me what your numbers are. Go ahead, take about a minute and a half to solve this. Yeah.
But it didn't matter because my calculator was that's the method.
So show me how you get around it then.
I just have
You
to
add
add
parentheses.
right.
Me too. Actually, I don't think I have to, but I just err on that side of caution because I don't trust calculators.
So I got 0.01238. So I got like
Here.
yeah.
Oh, okay.
So I got for
Okay.
the first one.
Instead of 140, you got a very small number. Yeah. It's annoying. But now that you know it, lean into it.
I do know.
Ashley and Ellie, did you guys collaborate on what numbers you got? Did you guys incur anything? How about Megan? Megan, did you work with Gabriel? Megan, where are you checking my Check with Jacob, see if you have the same number. You guys get the same one? You're working with the converting now you're working on figuring out whether it should be positive 9 or negative 9. Because they're going to go from big hertz to hertz, smaller intervals. Good. Meters. Good. Remember, gigahertz is just prefix unit. Giga being 1 prefix of hertz. So if you get out of giga, go to a bigger number, you're still at hertz. All right, guys, some things about units that might help you. If you're looking at your unit saying meters per second over per second, what cancels out? Well, per second cancels out, you're left with meters. But if that's confusing to you, you can rewrite meters per second as meters inverse seconds, meters times inverse seconds. Then, when you set up meter inverse seconds over inverse seconds, it's a little bit easier to see that you're actually doing inverse seconds divided by inverse seconds. So, if this is not conducive to your understanding of the units canceling, by the way, this semester I will lean into units so hard. Science is nothing without those units. If this doesn't make sense to you, lean into this. It is kind of that algebra exponent part of math, understanding that 1 over something is the same as something to its inverse. But lean into that, because that can help you just identify your units a little bit better. How many of you converted gigahertz to hertz? Did anybody not? Did you convert meters per second, meter hertz, into meta gigahertz? Meter gigahertz? Yeah, it's hard to say. No, I don't think so. And did you all get this number? 2.45 times 10 to the positive 9. How many of you went to negative 9? What did you use to keep track of which way to make your exponent? From big unit to small unit, from small number to big number. Watch your unit first because it will tell you how your number needs to change. And by the way, I rewrote my steps, but I skipped a lot. First of all, I took Lizzie's approach and I wrote lambda on the left-hand side without showing anything. I didn't do my algebra because at some point, if you don't need those steps, you should just move on. Now, we've got 10 to the 8th divided by 10 to the 9th. That's going to be something like 8 minus 9. I should expect my answer here is times 10 to the negative 1 meters, or just point something meters. So what do you all get? Say it out nice and loud. 0.
1, 2, 2.
And you stop there? Because 3 sig figs. If you already know when you're going to round, and you looked at that next number, 3, rounds down to 2. Good. Meters. What if I wanted to measure this and I don't have a meter stick at home? I just have a ruler and one side has centimeters and millimeters. How could I rewrite this number so that it's easy for me to read with a ruler? centimeters. Factor of 100. 2 decimal places over to make that factor of 100. This should be 12.2 centimeters long, or 122 millimeters. So I would recommend finding the videos on this and not just following my directions, but go home, take out your spinner, put a big chocolate bar in there, one that's at least 12 centimeters long, and you will see that the standing waves of the microwave etch themselves into a specific spot of your candy bar. That's actually the whole point of the spinner, is so that your food moves around through different parts of the wave. But you've maybe noticed this when you heat things up. The inside stays really cold while the outside stays hot. And that's exactly because you're seeing the node of the wave not reach the middle part of your soup, but hit the outsides of your soup, or not hit the middle part of your rice, but hit the outsides of your rice. Not spin fast necessarily. If anything, you should make it spin and move in and out, right? Because if you hit it just right, even spinning it might leave a dead spot right in the middle of what you have. So, microwave designers of the future, figure it out. Okay, questions on doing that math? Felt pretty easy? Your electromagnetic spectrum. I want to point out that there are maybe some things on here that you had never thought of as light before. I know we live in 2025, but how many of you listen to the radio at least once a week? Yeah, me too. Sometimes. Radio is light. You might think that you're listening for radio waves. Your car is actually looking for radio waves. Or rather, those radio waves interact with the material in your antenna in very specific ways. When you flip through radio stations, those numbers, 102.9, 107.1, those are the frequencies of your radio station. You could take those frequencies and convert them back into the wavelength that they're going through. How many of you have gone on a drive before and the radio cuts out after a certain ways into the mountains? How far? A good ways. You can get around some hills before you actually lose radio waves. That's because your radio waves are on the order of 10 to the second, 10 to the fourth meters long. Those radio waves are longer than some city blocks. So think about that photon is moving up, not the photon itself, but its wave is propagating up and then back down. By the time it hits one crest, it's moved more than a city block. That's huge. That's a huge propagation. That means that all the time you are standing underneath radio waves, and radio waves are always also passing through you. Because we've got Wi-Fi, we've got our cell phones. Those are using radio wave signals as well to communicate with the Wi-Fi boxes, with the cell towers. Luckily, those radio waves just don't interact with our matter, at least not in ways that we understand yet.
I work in the OR, and we're told that we are exposed to as much radiation in our environment as we are to an X-ray that we take intraoperatively. Is that what they mean? Like, is that kind of what you're saying?
Well, here's X-ray, which you can see is on the order of 10 to the negative 10 meters, so smaller than a nanometer. That is its wavelength. That's high energy radiation. So you don't want to be exposed to a lot of X-ray radiation, but the same amount of X-ray radiation is equivalent to a year's worth of other types of radiation.
So it's false, what we've been told.
Well, I guess I'm maybe not understanding. You as an operator standing behind the curtains.
No, so in surgery, like if we have like a big C-arm or a little C-arm, they say that like the little C-arm exposes us to as much radiation as we'd be exposed to in like our regular environment, so we don't have to wear lead aprons.
Oh, okay.
Does that make sense?
Yeah, that might just be how well it's been designed, so that the radiation is targeted and it's not loose. So that might not be an issue of the proximity you have to the X-ray, but a matter of how well the X-rays are actually targeted at the source. So you know that meme, like, don't worry, this X-ray can't hurt you, and then the doctors like run for cover, literally put on lead and then run away. I mean, you want to minimize how much exposure you're getting to high intensity radiation.
It's not bad like once or twice, but if you're a doctor like constantly doing X-rays, eventually that's going to cost you.
Correct. Or if you're Marie Curie and you're discovering radiation, then you can die early in your life because you've been exposed to so much high energy radiation. Scary stuff. Gamma rays, X-rays, ultraviolet, infrared. So I want you guys to do this quick. I'm actually going to turn off this projector. I want you to organize this list of light by increasing energy. Notice that I said also increasing frequency. Those two things are proportional to each other. The energy of the wave is proportional to the frequency of the wave. Similar to the energy of getting punched in the gut is similar to the frequency of getting punched in the gut. You punch me in the gut once a second, it's going to hurt a lot more than punching me in the gut once a minute. Higher frequency, higher energy. Okay, so red light, blue light, gamma rays, and microwaves. Organize these from highest energy to lowest energy, or from lowest energy to highest energy. Work with the people around you, too. Which ones feel obvious? Which ones do you have to debate on? I use a different way to tell red light. Just memorize it. But I bet you have a very intuitive way of thinking about it by relating it to other types of light.
Oh yeah, this is lowest. The lowest is red.
You know that blue fire is hotter than red fire? Yeah. Okay, that's good. I was going to use other types of light, not red light and fire. But another type of light that is kind of like red light is another type of light that is kind of like not literally, but you just say the body. Silver. What do you think is the highest energy frequency light here? Highest energy, highest frequency light on this list. Red, blue, gamma, or microwaves? You're debating between those two? Which type of light would you put in your kitchen? Would you use would you use an application, an appliance in your kitchen that emits gamma rays? One stray gamma ray is going to turn you into the Hulk. But you wouldn't be too worried about having microwaves, right? So does that help you change your mind? What's the highest energy wave here? Gamma, highest energy. What's the lowest energy light on this list? Sadie? Yeah, what's the lowest energy on this list? Microwave is the lowest energy light. And this might be kind of strange to you, but microwave actually makes water spin. The electromagnetic radiation interacts with the molecules and makes those molecules jiggle around. That's why you can get water to boil. But visible light doesn't interact with water. You can't boil water just using visible light, unless you have that magnifying glass and you can concentrate it and just get all of that energy into it. But a good way to think about this is that microwaves, very shorter than what our eyes can pick up. Now, the hard part. How do you distinguish what is lower energy, red light or blue light? How many of you said blue light is lower energy? Because you all looked at the notes. You guys did? You want to say why? Or you didn't? Oh, still debating.
If you stargaze or like even have a nightlight, like you're told to have red lights because your eye, there's less energy and less hard on your eyes, so you don't adjust as fast. Where if you have something blue, it's kind of the reason why phones and stuff cause some issues because they use a lot of blue light, and so your eye thinks it's warning. So blue light is a lot higher energy, and also the energy works on the scale. So red is the lowest, and then it gets.
So if you relate to that and you know that you want to protect your eyes from blue light, and that means blue light is higher energy, that's okay. I always thought the blue light glasses were to protect something about how you feel about sleep, your circadian rhythm, but not necessarily damaging your eyes because of its energy.
Not damaging its
So
eyes.
for me, it wouldn't help me understand which one is higher energy or lower energy. But if it does help you, that's good. It's not how I would get there, but I think we have a more intuitive way of getting there. So how many of you said that blue light is higher energy? Everybody did. Okay. Blue light is more similar to ultraviolet or infrared light. Why do you say that? Violet, blue, next to each other on the rainbow, right? Ultraviolet is what? Scary or safe? Scary, because it burns your skin. It's high energy. So blue light, high energy, because it's similar to ultraviolet. What about red light? Similar to another type of light? Infrared. Shares a name, right? Infrared light is literally the radiation that your body emits. Infrared light is the radiation that the Earth emits. When you're walking on the ground and you feel the heat coming off of it, when you're walking on asphalt and you get burned from it, there is infrared radiation coming off of it. You're feeling that infrared radiation. Fires emit red light, that's true. And its neighbor on the electromagnetic spectrum, fires also emit infrared light. So when you stand next to a fire and you feel that heat, that is infrared radiation that is hitting your body and warming up your body. Night vision goggles, heat-seeking glasses, those all look for infrared light. At my house, we have these cameras, so we can check on the cats while we're gone, and it has an infrared light that it shines, and so we can see in the dark. It's also kind of weird when we leave, our doorbell has that infrared light, and you'll notice that color, textures, they disappear in infrared because the materials are not interacting with infrared light the same way they interact with actual visible light. So, lower end, red light. higher end blue light. I want to fill in just a little bit more about this. This we said was low energy, low frequency, high energy, high frequency. What about wavelength? Long, we say. Long wavelength, low energy. Not necessarily a weak wavelength, still strong. What about here? Wavelength. Short wavelength, small wavelength. Oops, that's the wrong Greek letter. Small lambda, tight, because you're getting a lot of it per second. Energy correlates proportionally with frequency. Energy correlates inversely with wavelength. All right, why don't we take a quick 5-minute break before we talk about more on the energy of a photon?
What's your opinion on red light therapy?
Never heard of it.
Or it was it infrared?
Maybe.
Red light therapy? You've never heard of it?
Okay.
You know, you could go into literally
Sounds good. Make sure you watch the recording.
and I'm like, I feel like it's a hoax. Go into yeah.
Snake oil?
Yeah, I'm like, what is, you've never heard of it?
I never heard of it.
I'm shocked.
Red light therapy.
It's like,
Sounds.
people, I feel like old people use that, supposedly. Yeah, it helps with blood flow. It's supposed to help with blood flow or aging.
That's interesting.
Is that those masks? And like people spend, I don't know, a lot of money on these masks that go on your face.
Oh, where did I see that once recently? It was really scary.
Probably TikTok or something silly.
Yeah, well, it wasn't like an ad for it. It was like a movie or a show, and I want to say it was a celebrity wearing one of those masks. And yeah, I can see how like putting that red light right up against your face might do something,
But is it?
but I don't know what. I have a feeling it would surprise me if it was a bad thing. Is it actually what they're claiming? Maybe. Is it a peer-reviewed process? Probably not. But I doubt it'd be bad for you. You know, red light, heat lamps that you raise chicks under, right? Good for them. One, it keeps them warm.
Yeah.
I think that's it, actually. There's a lot of things that we do that may or may not be placebos, but placebos are not bad. Placebos are not bad things unless you're being taken advantage of for it.
Yeah, promotes healing, reduces what it claims, increases collagen and
Promotes healing. Doesn't cause healing. Just promotes it.
every time I see this. Yeah, I could see it.
And so when we made like the, or like, not the table, no, not the box next to it, it was like, it's this.
Okay. On this note of photons and waves, we introduced this idea of quantized and quantum things. All of you have probably heard of quantum mechanics, and that might sound daunting and scary, but quantum is related to the same word as quantity, quantitative, quantized. It just means an amount. Not just any amount, a specific amount. No more, no less. Just that much. And that's the process that we look at in this quantum mechanics section. We're looking at exact values that are required for certain things to happen. For instance, if you measure a photon, it will have a specific energy, a quantum. And this is the equation that we get for it. Good job. E equals HV. Not HV. You threw me off. H nu. This is the energy of a photon. What is H? Oh, you even said it right. Good job. It's not Planck, but you can say Planck. I won't judge you out loud. I think he's German, definitely European from somewhere. So pronounced it Planck. This is Planck's constant. And I don't need you to memorize this number either. Not that it's hard to memorize. Once you've done it a few times, you're usually good to go. But where will you find this if you're not going to memorize it? On that useful equations sheet. It's always given to you so that you never have to guess. This is 6.626 times 10 to the negative 34 joules seconds. J there stands for joules. Joules is a unit of force, so it's work that's being done. There are going to be instances where we don't want joules, and we'll talk about how to convert joules into different units. Joules is actually just 5 units in a trench coat. There's another way that we can write this equation. E equals H nu. Nu is equal to C divided by lambda from our equation earlier. Nu equals C over lambda, which means that we can also write this equation as E equals HC over lambda. And you'll see that both forms of that equation are given to you, so you don't need to memorize which one is which. But this does save you some time. If you're given the wavelength, you don't need to do the process of converting it into frequency first. You can just plug it in with the speed of light. If you have the frequency, you can just plug it straight in. So let's do some calculations. Let's find out the energy. By the way, I'm putting these as question marks because I don't like to put X all the time. And I like to leave that variable as itself. Let's find out the energy given Planck's constant when the frequency, what did we find earlier? Let's find that energy of the photon from our microwave. Our frequency is 2.45 gigahertz. What was step one earlier when we were going through that calculating wavelength? Write the equation. Step one, E equals, which form do I want? H nu or HC over lambda? H nu. Step two was do some algebra. Do I need to do any algebra here? It's actually already set up for me to solve for E, so I don't need to divide by anything. Then I just move on to step three. So I'm just going to cross out 2 because I don't have anything to do. Step 3 is plug in the numbers. 6.626 times 10 to the negative 34 units, joules, seconds. Do you think it's useful for me to put in 2.45 gigahertz? Will it get my units to cancel if I put in gigahertz? Good. So I'm not going to put in gigahertz. Since we already did the work here, we know how to convert gigahertz to hertz. So I'm going to automatically change this to be 2.45 times 10 to the 9th hertz. And notice when I put it in down here that I can write that as inverse seconds. Because my unit for Planck's constant doesn't say joules inverse hertz, but it could. Could be 6.626 times 10 to the negative 34th joules per hertz. Because hertz is inverse seconds, which means seconds is inverse hertz. Inverse hertz is per hertz. But I'm deciding to change hertz just to inverse seconds because when I multiply joule seconds by inverse seconds, seconds cancels. S to the 1 times S to the negative 1 is S to the 0 is just 1 seconds is gone. Does that make sense? What unit should I be left with when describing the energy of a photon? Just joules. Is this going to be a big number or a small number? Very small number. Very small. So let's plug that in and see what we get. Remember, if you're finding out that your exponents don't work well, put in parentheses to make sure that things don't get confused. How many sig figs should I round to? Based on that 2.45. Alina, do you have yours? Okay, can we put it in scientific notation, which means no 16.2. It has to be between 1 and 10. Good job. That was really a challenging one because you needed to take 16.2 times 10 to the negative 25th and actually make that exponent smaller because that's what it matches on my phone. Because you moved your decimal place to the left, which is one place closer to actual 0. So that means you're closer to 0, a smaller negative, less negative. Anybody get a different number? Good. Now, to put this in the context of what we didn't get to do much last week, let's say that I get exactly 1 mole of these photons. Here's a trick. Watch this. How many units does this have? 1? 3? Oh, 5 units in a trench coat. Masquerading as 1. It's 1 unit, joules. Watch this. How many units now? 2 joules per photon. Photon is counting as a unit because it's a thing. It's a label. I could say joules per molecule, joules per car, joules per whatever, and that now counts as a new unit, joules per mile. I don't know why anyone would do that, but we can do it. Here's why this is useful. I don't know how to take that number and turn it into the energy of a mole worth of photons. But I do know how to convert 1 photon into a mole's worth of photons. So here's what I set up. 1.62 times 10 to the negative 24th joules per 1 photon. Would you guys agree I didn't do anything illegal there? I didn't do anything illegal. That is what it was saying already, just quietly. I'm saying the quiet part out loud, per photon. How many photons in a mole of photons? Now I'm doing dimensional analysis to say, what if I didn't have just 1? What if I had 100 million, billion of them? Do you guys agree with this setup? Does this work? Is this allowed? Why did I put photons on top and moles on the bottom? So that photons cancels, and I now get into the units of moles. What number goes on top and bottom? Good. Big unit, small number. Small unit, 6.022 times 10 to the 23rd, big number. Now we just have to plug it in. I told you were going to get some exercise work on your calculator. If your calculator is nice, you might be able to just grab that number from your previous calculation and just multiply it by Avogadro's number. Can you give this to me in scientific notation with the correct number of sig figs? Feel like you have it? Not yet? Who's got it? Other than Ryan? No shit. Jacob? 9.75 times 10 to the negative 1. 9.75 times 10 to the negative 1. Oh. One very important part. Joules per mole. Nice. By the way, we're going to abbreviate moles this semester as MOL. What a useful abbreviation. Moles is mole. Molecules is not mole. Nothing else gets abbreviated as MOL, just moles. Great job converting that into scientific notation. It wasn't almost useful, right? It might actually be easier to interpret as 0.97 joules. We don't even have 1 joule yet when we bombard this with a mole of photons. Okay, whatever a joule is, we don't have 1 of it. Now, did anybody get a slightly different number than Jacob? Ashley, what'd you get? So, Jacob, did you plug in 1.62 times 6.022, or did you plug in 1.62337?
I did 1.62 times 6.02.
And Ashley, what did you plug in? The number that was already in your calculator? 1.62337?
If you plug the number that's already in your calculator, you'll get like 0.9775.
Because I got the same as Ashley. I got 9.775, which would have rounded 7 to 8. But I suspect that if you plug in 1.62 times 10 to the negative 24th times 6.022 times 10 to the 23rd,
Yeah, 0.9755.
now you get 9.755. Oh, so it does still round, huh?
Yeah.
It should round 9.7. Do you agree with that, Jacob? 9.755, 9.76. That's a rounding thing.
6.02 instead of 22, it doesn't round up.
Yeah, it gives you, if you do 602 instead of 22, it's 0.9752.
I see. Okay, so if you lob off that last 2, it changes your number. Why would we ever lob off that last 2? I think that number's on here too. We should check.
It is not.
It's not on here. Okay. That's odd. I wish there was a definitely useful, but it might be on the final sheet. No, I don't think it is. Well, here's my advice then. Don't lob off that second 2. But I do still want to point this out. If you rounded 1.62, you do get a different number than if you plug in what the calculator gave you without rounding. And that's a rounding thing. So if you get onto the exam and you need to do multiple calculations to get to the final answer, don't round in between. But keep in mind that if you're doing multiple calculations and you're being asked to plug in with significant figures each one, then there may be some small differences. So if I was on the exam and I saw 9.77, but I got 9.76, as long as all of the other answers are very much obviously incorrect, I'm going to say it was just a rounding issue, and I'm going to take 9.77. Because that last digit is what? Uncertain anyways. So if I'm off by 1 or 2 values, yeah, that seems within certainty. Uncertainty, certainty. Any questions on this? Calculating the energy of a photon? So going back to that video that we watched earlier, here's what's cool about photons. Photons interact with electrons. This idea that photons interact with electrons was first developed and understood through the photoelectric effect. Those of you that did your reading, anybody want to try and summarize the photoelectric effect? And that's actually the idea of quantum, is that you get this packet of energy. Each photon has a specific energy. If you hit a piece of metal with a photon of at least a specific energy, you can eject an electron from that metal. How would you know that you've ejected that electron? You can see sparks fly, right? So here's what they did in this test. They took a piece of metal and they hit it with super high intensity, high amplitude, low energy light. Nothing happened. Then they hit that same piece of metal with very low intensity, low amplitude, like just one photon, high energy light, and sparks flew off. This told them it doesn't matter how intense the light is, how many moles of photons you're providing, the specific frequency of the photon matters. The specific energy of the photon itself matters. So they posited that if you meet this minimum energy threshold, then you can eject an electron. It's like that electron is sitting in a well, and unless the specific energy, the specific amount of the photon matches that energy well, it doesn't come out. Then, if you hit more than that, the electron gets kinetic energy. Doesn't matter how many photons you provide, the photons themselves have to match that energy gap. If the photons have more energy than that energy gap, then the electron gets out of its well, stripped away from the metal, and then gets kinetic energy to fling off into space. That's the photoelectric effect. So they started trying to figure out what is going on. What is this relationship between light and matter? Why is it specific on the energy of the photon? Now I want to talk about two things that also highlight this relationship between matter and electricity. Or sorry, matter and light. One of them is black body radiation. I like to think of this as kind of the opposite of the photoelectric effect. Don't shove a photon at a piece of metal and see what energy is required for an electron to come out. Instead, make that metal really hot. Get it moving around so much that its electrons are going up into high energy states on their own. And when those electrons come down from high energy states, they release that excess energy in the form of light. So these heated samples, they give off a continuum of light, depending on just how high that electron got before it fell down. It will give off different specific energies. This is what you get when you heat a sample, something like the sun. The sun is a heated sample, and it emits black body radiation. If you look at its black body radiation curve, you'll notice these two very strange peaks in it. And that's because you're analyzing the continuum of light emitted from the sun from the surface of the Earth. And there are two very specific frequencies of light that water is really good at absorbing. So you don't see those frequencies when you're observing it from the surface of the Earth. This is the sun's black body radiation spectrum. But you can make an easier black body radiation by just taking a metal sphere and heating it up. What happens when you get that metal sphere hot enough? Starts glowing. if you take that light and you put it through a prism, somewhere where the speed of light changes, so each frequency of light starts to change differently and they separate from each other, then you can see the continuum of frequencies that are emitted. Something similar to this but very different is line spectra. This is when high voltage in gases give off discrete photons. Discrete there just means specific. Not higher, not lower, this one. Only this one. This is what we saw this morning. All of those different gases gave off different discrete photons. So we look at this line spectra by taking that light, that purple, that green, that blue, whatever it is, putting it through a prism, and instead of getting a continuum, I'm going to put my unit here as lambda. Instead of getting a continuum of light, I get so much light at different wavelengths. I get the most of this light emitted. I get the least of this light emitted. Instead, against different lambda, you get very specific frequencies that are emitted. This wavelength is emitted. These wavelengths are emitted. This wavelength and this wavelength, but not all the way throughout. Do you see the difference between black body radiation's continuum and high voltage gas line spectra? They look different. Notice that the unit is the same. This has a ton of different values. This is discrete. And this is what you see on this PowerPoint slide. Which of these is black body radiation? This is black body radiation. Heat up a coil of metal inside of a light bulb, and you get a continuum of light frequencies, of wavelengths. The entire spectrum is produced. Which of these is a line spectra from a high voltage gas? The bottom one. Notice that the wavelengths are all the same, or you're looking at the same spectrum from purple to red. But here, this magenta gas that you're looking at is just comprised of 4 discrete photons. And then you get into color theory and how all of those mix to give you the gas that you're seeing. So if I showed you that video again from this morning, I wouldn't expect you to be able to see this and tell me, just based on the color, which gas is which. What would you need to do first in order to, without the labels too, what would you need to do first to figure out what sample belongs in each tube? Sorry? I can't tell just by looking at this combination of all the colors. I need to put this light into a prism and get the specific line spectra for each of these. They'll all be different. Even these two that look pretty similar in color, they'll have different specific discrete photons. That is a very useful tool. We have an instrument upstairs called the ICP-OES, Inductively Coupled Plasma Optical Emission Spectrometer. And our ICP-OS, OES, looks for this. It turns samples into plasma, which is ionized gas. And it looks at the energy that comes off of them. And it says, this is the element that produced the line spectrum I just saw. Then it heats it up again and says, this is the other element, and this is how much it is based on the intensity of that light. Calculates how many moles of those photons are being hit, and tells you how many atoms must be there to produce it. Very useful. Questions on this? Black body radiation, line spectra. What's the singular of spectra? Spectrum. So spectrum, plural, spectra. Photoelectric effect, interaction of light and matter. Where does this light come from, the continuum, and where does this light come from in the line spectra? Sorry? Where in the material, regardless of what the material is, what is producing the light? Electrons are producing the light. All of this light comes from electrons. In the same way that the photoelectric effect describes how light can make electrons move. Are you guys okay with all of this? The fact that light and electrons are buddies? That they are reciprocals of each other? Light can make electrons move, and electrons moving makes light? Do you remember earlier I said that you are emitting a certain type of radiation? Do you remember what? You're emitting infrared radiation. What is infrared radiation? Light. And where is that light that your body is emitting coming from? Your electrons. Specifically, probably, the electrons that are in bonds that are vibrating or bending and then being run into something and caused to stop their stretching or their bending abruptly. And where does that extra energy go if it can no longer vibrate or bend or stretch? Emitted as light. So I do want you to think about that when you try to sleep tonight. Your electrons are emitting light as you sleep. And I'll put you into my ICP OES to figure out your line spectra. I would never. All right, the last thing we have to talk about in this module 5 is the Bohr model of the atom. Boring. I only say that because he's wrong. Otherwise, if he wasn't wrong, I wouldn't make fun of him for that. And it's a terrible way to view it. Don't. No. Actually, Bohr jumped off the back of Rutherford. Do you guys remember Rutherford? Ernest Rutherford? What did he help us decide? Rutherford had the gold foil experiment. He shot alpha particles, which are really just helium nuclei with no electrons, 2+ nuclei. Shot them at gold foil and found that the plum pudding model didn't hold. These alpha particles were flying straight through, as if they were going through empty air, and occasionally deflecting and bouncing straight back even. So Rutherford decided that there was a nucleus in a mostly empty atom. So this is what Rutherford said. Nucleus, positively charged, and around the nucleus is the planetary model. Here's an electron, some more electrons out here, And what are these electrons doing according to Rutherford? They're just orbiting. By the way, I'm not being specific about the number of electrons I put in anywhere. Just random. I'm just saying these electrons are just spinning around the nucleus like planets spinning around the sun. That's what Rutherford posited. But Bohr came in and said it's not totally random. Bohr says that these energies are specific. Orbits have specific energy. An electron that stays in one orbit does not emit any light. But an electron moving between orbits must absorb a light equal to that energy difference, absorb a photon equal to that energy difference, or emit a photon equal to that energy difference. Electrons absorb photons equal to the energy difference or emit photons equal to that energy difference. Notice here that I'm using a triangle, which is the Greek letter delta. You might recognize that it is the shape of river deltas. Delta E means change, difference. The difference in the two energies. And Bohr, by the way, is not right. But he's also not wrong. He's, how do you say this? He's getting to the right answer incorrectly. So there's some useful things that we can study based on this, primarily the line spectra, but he's confused. He thinks the atom still looks like this, and he's very wrong. So we get this equation for the energy of a shell. En equals negative k over n squared. N is an integer value. K is this constant, 2.18 times 10 to the negative 18th joules. And together it gives us the energy of a shell. The first shell gets n equals 1. The second shell gets n equals 2. Third shell, n equals 3, etc. You can see that with each increasing integer squared in the denominator, the energy gets smaller, closer to 0. I take this k divided by an ever-increasing larger number. When I divide by a larger number, I start getting closer and closer to 0. Do you agree with that? What does that mean? Which electrons have the highest energy? Electrons closest to the nucleus have the highest energy. Why would that be? They're being flung around super fast. They've got the strongest electromagnetic attraction to that nucleus. And I do want to clarify, by highest energy, this will be the most negative number. Highest energy represented by the most negative number. But the really useful part here is getting the difference in energy shells. And just for the last time, because we're going to have to head out after this, this equation, the difference in energy, is found on your sheet as well. And I recommend learning it and how to plug it in, I'm going to give you a small change here. When you take the difference in energy, you can actually factor out this negative K constant. So you get negative 2.18 times 10 to the negative 18th joules times 1 over n squared minus 1 over n squared. Look at how it's written on here, n1 minus n2. I don't like that. Here's how I recommend putting it. nf minus ni. Final minus initial. Where is it ending up? Where is it starting? You guys have enough today to wrap up Module 5 tonight, your Module 5 checkpoint. So I want you to try and do that. But we will pick up on Wednesday solving for some of these equations, because I do want you to make sure you feel comfortable plugging them into your calculator. So we'll pick up Wednesday here, and we move into Module 6, more on quantum theory after this. Have a good night, a great day. Take care.